This is lesson 15 of AS Pure Mathematics. Today's topic is differentiation. You can show this through limits, however, considering this is short, I'll use the gradient. To find the gradient at a point, you can draw a tangent to a curve and find the gradient. However, this only gives you an approximation. So what if we made it super accurate? Here's where we use the gradient function, dy dx. This means we can find the gradient at any point by substituting in the x value. If we take this general form, then the gradient function is equal to the power multiplied by x to the power of the previous power minus 1. If there is a constant besides the x, then it doesn't change the rules used. This also means we can find the equation of a tangent to a curve at a specific x point, since dy dx will equal m. Also, here's a reminder of how to find the gradient of the normal. Here's an example of finding the tangent and normal of the curve when x equals 2. Let's have a look at the stationary points. This is when the gradient is 0, therefore when dy dx is 0. So to find a stationary point, you just solve for x after you find the derivative and set it to 0. However, how do we tell if it's a maximum or a minimum? This is where we use the second derivative, d2y over dx squared. Same as before, this is just finding the derivative of the first derivative. After solving for x when dy dx is 0, then substituting that value into the second derivative. If that value is greater than 0, then it's a minimum. If it's less than 0, then it's a maximum. And if it's equal to 0, then it's a point of inflection. The last thing we will look at is its practical applications. This gives me the chance to mention that dy dx means that we are deriving y with respect to x. Therefore, in this equation, we are deriving the equation for the area with respect to x, to find the maximum area if the perimeter is 400 meters. A derivative of a constant is 0.